Welcome to the video lecture series of operating system. In today's session, we are going to start a new topic which is nothing but a process synchronization. Myself Kunal Panchal, your instructor. In this particular session, we are going to discuss process synchronization, in which we will discuss two topics. One is race condition and second one is critical section problem. So let us discuss first process synchronization. So before going to discuss process synchronization directly, what we need to understand first, why this process synchronization is required, okay, and what it means actually. So as you know very well, what is process? Process is nothing but program in execution. Now, in the case of multi-programming operating system, in which there are more than one processes are ready for execution and they are located into a main memory. So definitely between these set of processes, synchronization should be proper, or synchronization should be, we can say, there. Okay, so there should be some ordering between this processes so that it won't lead to inconsistency at the end. So to avoid inconsistency, the process needs to be synchronized in a proper manner. So this is the significance of process synchronization when we are talking about multi-programming operating system, or we say multitasking operating system, in which more than one processes are ready for execution. Okay, so which process needs to be executed first, then after which one should be next. Okay, so that sequence, that ordering is very important as far as multi-programming operating system is concerned. Yes, so let us discuss these things with the help of one example. Suppose in this particular figure we have P1, P2 and P3. There are set of processes which are ready for execution and which are located into main memory right now. And say for example, and P1 and P2, this P1 and P2 process wants to access R1 resource. So in this particular figure, there are two type of resources we have, R1 and R2, and both the resources are shared in nature. Okay, so if P1 and P2 wants to acquire R1 resource at the same amount of time, this situation needs to be avoided. Okay, if you want to make it proper synchronization. So definitely R1 is shared resource, so everybody can access that resource, but it should be accessed in a mutual exclusion fashion only. Then and then it won't lead to inconsistency. Okay, so for example, if you are talking about printer is shareable resource, but means what, it can accept more than one request at the same amount of time, but printer can satisfy only one process, or we say one request at a time, even though it is shareable resource, but it should not be used in a shareable mode. Okay, and if you allow to access in a shareable mode, definitely it lead to inconsistency. So printer can accept multiple requests at the same amount of time, but at a particular amount of time it can execute only one process only. Okay, so to achieve this criteria, when we are talking about software resources, or we can say hardware resources, that needs to be arranged in a proper order. Okay, so to avoid inconsistency. So let us discuss that stuff with the help of one example. Suppose in this particular figure we have two processes, P1 and P2. These things you need to keep in your mind, and one program we have. These two processes and one program. Program is nothing but we can say software resource. So this program needs to be accessed by this P1 and P2 process, okay, in a different order, or we say in different nature. How? That we are going to discuss in upcoming minutes. Okay, so this program, or we say process contains, this program contains set of instruction in which first one is read of A. R stands for read operation and W stands for write operation. So A is nothing but a shareable resource, we can say. This is nothing but a shareable resource, and it is software resource, it is not a hardware resource. So resource A needs to be accessed by P1 and P2 process in a different way. Let us discuss. So first instruction is R of A, means what? Read of A. Then once you read that value of A, and what is the initial value of A? For ease of understanding, we have taken the initial value of A is equal to 10. Okay. Once we have the value of A, then this program will simply increment the value of A by 1. So A is equal to A plus 1 means if you add one value, okay, in initial value of A, definitely the answer would be 11, and then we are writing that value in the secondary memory. Okay, so that write of A is nothing but to store that value in a memory permanently. Okay, so this set of code we have in this particular program. A is nothing but shared resource, and initial value of A is equal to 10, and this P1 and P2 process wants to access this set of code for its own purpose. So what will happen in this case? Suppose this P1 and P2 executed task in this order in which P1 is followed by P2. If P1 is followed by P2, definitely first of all P1 would be executed. Okay, so P1 will access this code. So P1 will start its execution. It will fetch the initial value of A. A is nothing but 10. Then it will increment the value of A. So now value would be 11, and 11 would be written in the memory. So if P1 is executed first thoroughly, in that case the output of P1 would be, value of P1 would be 11. Now once P1 completed its task, then P2 started its execution. Means what? There is a systematic order in which these two processes are executing. In that case, it won't lead to inconsistency, because at a particular moment of time, even though this A is shared resource, but we are accessing this resource in a mutual exclusion fashion. So that's why it won't lead to inconsistency. How? P1 in this particular example, P1 is executed successfully. Now P2 will start its execution. Now what is the initial value of A in this case? Once P2 starts its execution and read the first instruction, read of A. So in this case, value of A would be 11. Initial value of A would be 11, and then it will be incremented by 1, and then the final value of A in the case of P2 process would be 12. So you can this logic is very simple. You can simply imagine, if you are executing this set of code 2 times, definitely the answer would be 12, because initial value was 10. So if you are incrementing this initial value by twice, okay, definitely the answer would be 12. So in this case there is no problem, in which P1 is followed by P2 or P2 is followed by P1. In both the cases there is a serial execution of transaction, or you can say these processes. So definitely there is no inconsistency. But what will happen if these two processes wants to access this resource, okay, or you can say resource A in terms of this example, simultaneously? In that case it may lead to, I'm not saying it always lead to inconsistency, it may lead to inconsistency. How? Let us discuss. Suppose for example, in the case of multi-programming operating system in which more than one process are ready for execution, there are definitely context switching would be there. Okay, so say for example, suppose P1 started its execution and it read the first instruction of this program, and this is nothing but read of A. So what is the initial value of A? 10. So it will be read by the P1. Now once P1 executed this R of A successfully, now at this particular control, it will context switch to the P2 process. Means P1 suspended its execution for a while, and it will give the chance to P2 for its execution. Now once control is shifted to P2, now P2 again will execute this set of code in a serial manner. So P2 will fetch what is the value of A in this case. Definitely P2 will fetch the initial value of A, which is nothing but 10 in this case, because the value which is read by process P1 is not written in the secondary memory. So that is the reason why P2 also fetch the initial value same as P1 has fetched in the previous case. Okay, so the P2 will fetch the initial value of 10, then it will increment its value by 1, and it will execute the write of A instruction. Means what? Now the final value of P2 is what? 11. Okay, so because P2 started its execution and it completes its execution without doing context switching. Yes. Now once P2 is finished its execution, now control switch back to a P1 process, because the execution of P1 was remaining. Okay, so these two instructions needs to be executed, okay, because it was remaining in the first go. Okay, now once control is switched back, so the second instruction would be executed first. So A is equal to A plus 1. Now in this case, which was the value of A, which is read by P1 process initially, so it is nothing but 10. So it will increment its value by considering the initial value of 10. So 10 plus 1 is equal to 11, and it will simply write a value in the secondary memory. So what will happen in this case? P2 actually, if these two processes execute this set of code two times, definitely the answer should be 12. But instead of 12, at the end we are getting 11 in this case. Means this leads to inconsistency, and this inconsistency problem is nothing but race condition in process synchronization. Okay, if we are allowing more than one process are trying to access the same code at the same amount of time by having the context switching scenario, as I told you, it may lead to inconsistency. So actually the answer should be 12, but instead of 10 we are getting 11 in this case, and that problem is nothing but race condition, which is very important for your examination purpose. Okay, now the next problem is critical section problem. What it means actually? What is critical section? First of all, so in this particular figure you can see there is one program which contains set of line of codes we have. Okay, I have not written the code of this program because we need to understand this concept of this critical section. So during its entire code, or you can say address space, a program may have at a out of total address space, some address space program using its private resources for execution. Yes, so some of the portion means some of the line of code would be accessed by this particular process by having the private resources. Means if process using its private resources for its execution, in that case it doesn't matter in which order they are accessing or it access that resources, because it's that resources are its private resources, so order in this case won't matter. Yes, but if this process using shared resources at a particular moment of time during its execution, in that case it may lead to a problem. So that problem needs to be resolved. So what is critical section? A critical section is nothing but a line of code which would be exist in a particular process while that process trying to access the shared resources. So that area would be considered as critical section. Okay. Now, when problem occurs when a process, any process wants to access shared resources. Yes. Means what if more than one process are compete to access shared resources, definitely in that case this problem can occur. Like it may lead to inconsistency. So to avoid inconsistency, what we need to do is, even though multiple processes are competing for a same resource at same amount of time, still we need to have certain criteria that needs to be satisfied so that we can give guarantee to you at the end it will never lead to inconsistency. So what are those criteria? Let us discuss those criteria. But before that, you need to understand what is critical section. So critical section is a part of code in which process is trying to access the shared resources. Okay. So to avoid this, because in this case there are chances of inconsistency. So to avoid this problem, because in real life scenario, suppose there are two types of resources, private and public resources, we can say. Okay, so shared resources we have. So private resource, suppose at your home, if you are using your television or a mobile phone, irrespective of the order of execution, it won't lead to any problem, because that resources are private resources. Okay, you are the owner of that resources, so nobody can use your resources because that resources are private. Okay, but when, say for example, if you are using your bus or a train, these are the public resources. So in that case, there should be some ordering needs to be finalized, or there should be some rules and regulations needs to be enforced to avoid the collision. If you are using bus or train, which is nothing but public resource. So when we are talking about shared resources, in that case problem may occur. So how to resolve this problem in the case of multi-programming operating system? So what are the criteria that needs to be satisfied anyhow to avoid inconsistency at the end? So these are the criteria. These three criteria needs to be achieved at the end. So first one is mutual exclusion. As I told you already, mutual exclusion means even though two, or can say more than two processes are competing to access a same resource at a same amount of time, even though this situation is happening in this case, still at a particular moment of time, only one process can access this shared resource, or we can say only one process may, or we can say must enter into a critical section at a time. It means, I am concluding this argument. What is mutual exclusion? Mutual exclusion means what? If more than two processes are competing to access the shared resources, means what? When a process can access the shared resources, when it enters into a critical section, and when it enters into a critical section, if that process follows these three criteria. Okay, so for example, if two processes are trying to enter into a critical section, so as far as mutual exclusion property is concerned, only one process can enter into a critical section at a time. That is nothing but mutual exclusion property, means one at a time. If you want to conclude that argument, one at a time means only one process can enter into a critical section at a time. If you are following this strategy, definitely there is no collision and there is no inconsistency at the end. So the mutual exclusion property, or say criteria is mandatory. Okay, so that is the reason why I have highlighted in that particular point into a yellow color. So it is highlighted point, means what? This is nothing but mandatory criteria. Okay. Second one is progress. Second criteria is progress. So what progress means actually? So like in this particular figure, we have three processes P1, P2 and P3. And if I am executing this P1, P2, P3 into a round robin fashion, in which all the processes will be executed for a fixed period of time only. That we have understood already in the process management chapter, in which we have discussed round robin CPU scheduling algorithm. So you know very well how round robin algorithm works. So if we are executing this set of processes P1, P2, P3 in round robin fashion, okay, so what will happen? So what progress tells us? So if you are strictly following this round robin fashion as far as these three processes are concerned, so there are chances out of means what, in this case we are assuming whatever the available processes we have in main memory, all the processes would be executed in round robin fashion, so that it won't lead to inconsistency. But there is one problem. Definitely, if you are not following progress, okay, it won't lead to inconsistency. But that task is not efficient. Why? Because if we have 10 processes in main memory, and if we are executing all the processes in round robin fashion, there are chances out of 10 processes, say for example 7 processes are not required to enter into critical section. Means that it means what? These 7 processes don't want to access shared resources. It is not required for execution. In that case, what will happen? If you are following this round robin fashion for all the processes strictly, it means what? Even though 7 processes do not require shared resources, still we are putting that processes into a critical section to access the shared resource, even though it is not required. So that task is not efficient. So what progress tells us? We will consider those processes only which wants to access the shared resources. That set of processes we will enter into a critical section, and that property is nothing but progress. Again, this is the mandatory properties. That is the reason why I have highlighted that second point. So these mutual exclusion and progress two are mandatory to avoid inconsistency in multi-programming operating system. Now the last one, bounded wait. What bounded wait means? What will happen in this case? Suppose if any particular process wants to enter into critical section to access the shared resources, but for very long period of time that process do not, or we can say it is not able to enter into critical section for long period of time. So there should be some time limit. Okay, it should be finalized, so that these means what, this process should not be starvation should not be possible in this case. So to avoid the starvation, the third property, bounded wait, needs to be satisfied. Okay, so we need to set some time limit, and after that time limit we can go for aging technique. We can increase the priority of that process, and again we will wait for 10 minutes, and again that logic we have already understood in the process management. Okay, so bounded wait is an important criteria, but that criteria is not mandatory. Okay, it is optional criteria. If you satisfy that criteria, it's well and good. If you do not satisfy this criteria, it's okay. It won't lead to inconsistency. Yes. Okay, so these 3 criteria needs to be achieved anyhow to avoid the critical section problem. And once you avoid this problem, definitely the system won't lead to inconsistency. Okay, so in this particular session we understood the significance of process synchronization, what is race condition, what is critical section problem, that we understood in this particular session. So I hope it was clear to you. Thanks for watching this video. See you in the next one.